Hello, my name is Ernest Heimseth and I am a principal scientist at BioTek Instruments. I hold a PhD in biochemistry with expertise in cell biology and light microscopy. Today we will discuss the colony formation assay, which evaluates the proliferative capacity of individual cells. This assay is essential for cancer research, allowing drug screens and radiation dosing to be conducted. Conventionally, this assay is performed in each well of a multi-well format. Analysis of this assay involves scoring and quantifying colonies manually by eye, which limits throughput capabilities. Using the Citation 7 cell imaging multimode reader, we've developed automated methods for conducting a colony formation assay using both fluorescence and upright bright field microscopy. Gen 5 software enables colony counts to be easily compiled and analyzed. In this instructional video, I will discuss important aspects to consider when preparing sample plates for imaging. I will then walk through how to configure Gen 5 to image, analyze, and build a dose-response curve of an anti-cancer drug from the colony formation assay. We will begin the tutorial by imaging colonies using the inverted fluorescence microscopy. First, open Gen 5. In the task manager, make sure that the experiments is highlighted and select Create New. And then on the left-hand side, select Procedure. And first, select the plate type that you will be imaging. In this case, we will use a CoStar 96 well clear bottom black side with a product number 3904. We will not be using the lid, so deselect that. Under Actions, select Image. Because we're using the inverted imager, select that as well. Now, for the tutorial purposes, we will not be reading the entire plate. We will be focusing on a select well. We will be imaging using 4x magnification, and be sure to select the wide field of view option. For fluorescence, we want 2 channels. We're going to want Texas red as the first channel, and DAPI as the second channel. Now, instead of auto-exposing, we're going to manually determine our exposure settings as well as our focal heights. Because the 4x objective only does not cover the entire well, select the montage, and by default, we will be choosing a 2x2 montage, which will cover the entire well. Additionally, select the crop image to size of well. What this will do is eliminate the area of the image outside of the well for analysis purposes. Now, to adjust your exposure settings as well as focal height, go back to your channels, and under the Texas red, select the microscope icon. Select our well of interest, D4. Now, you may not see anything right away. The crystal violet fluorescence signal is rather faint. However, there's plenty of signal for our purposes. What we'll first have to do is just increase the LED intensity to 10, our integration time to 500, and our camera gain to 30. Now what we want to do is determine our ideal focal offset. By this, we'll just use autofocus. Okay, so we've determined our focal offset to be, or our ideal focal height to be 3385. And because we're going to use this number to determine the laser autofocus setting, we want to make note of this number, 3385. And once we're done here, save these settings. Now that we're back to our settings page, now verify the focal height and exposure settings for our DAPI channel. We can first start with the camera gain. And we'll reduce this down to 50 milliseconds. A useful tool is to use your line scan to determine whether you have sufficient signal or not. What we can do is just draw a line across a few nuclei to see whether this is sufficient signal. And on a 16-bit camera, our maximum amount of gray values is 65,534. And as you can see, as we've drawn a line across these two nuclei, we've pretty much covered our entire dynamic range. So I think these settings are sufficient to get maximum signal. And so we'll keep the settings here. Now, just by visually assessing, it looks like our focal height is sufficient for what we'll need. So save these settings. Now what we want to do is use that focal height to set our autofocus. So instead of using the default focal method, what we want to do is deselect that, and then in the drop-down menu, select your laser autofocus setting. At this point, you'll be prompted to enter a valid reference scan. So hit yes. So what we want to do is go back to our well of interest, manually enter in the focal value that we determined, which is 3385, apply, and save these settings. At this point, a reference scan will be acquired. Now we want to double check the focus options for our DAPI channel. And we want to make sure that the focal height is selected relative to the first channel with a 0 offset. We'll center our images again, then hit OK. Now we're ready to image. So hit OK again. And then click the Read New icon. For this, you'll be prompted to save the image files in experiments. So we'll go ahead and overwrite this one. Colony information assay, inverted fluorescence. Once our image is acquired, we can then select the thumbnail for the well of interest that we've imaged. What you'll first see is a low resolution view of the well in the montage setting. The first thing we want to do is stitch that 2x2 montage. So select the process step and set up a new image processing step, image stitching. Select a text as red as a registration channel and be sure that the linear blend is chosen for the fusion method. We want to keep the crop stitch image to remove black rectangles around the borders. And we want to downsize the stitched image. However, we'll only downsize it to 50%. Select OK. Now what we're looking at is a stitched single image of the entire well. At this point, what we want to do is add this step in the case that we have multiple wells that we want to apply the same pre-processing step to. Once you do that, we want to undergo a background subtraction. For that, go back to your process step, set up a new image processing step, and select image pre-processing. The window that you'll see gives you two options for your two different channels. Starting with the text is red, you're going to apply an image pre-processing step. Be sure that the background is set to dark and that you will be undergoing background flattening. However, deselect the auto function. For this one, we will be determining our own rolling ball diameter. Because these colonies are rather large, I like to set a rolling ball diameter of 2,000 microns. And because for the sake that we want to be able to identify colonies as intact objects instead of the individual cells within it, one thing that helps doing that is to apply image smoothing strength. So for this, we'll set it to 5. Again, a useful tool to use during this entire process of both imaging and pre-processing is the line scan. And if you draw a line scan across one of these objects, what we're looking for is, we deselect the DAPI channel, is we want a continuous signal that does not dip below background across the entire object as seen here. And we can look at different objects to verify that this is in fact the case. And this is going to be important when we come to the step of identifying these objects as intact colonies. So now that we're satisfied with the pre-processing parameters for the text is read, we can move to the DAPI channel. Again, we're going to apply a pre-processing step. However, we're not going to be using those same settings as channel 1. We are going to do a background flattening. However, because we want to be able to identify individual nuclei, we want to be able to background subtract a much smaller area. And for this, what I like to do is use something that's slightly smaller than the diameter of your average nuclei. So we're going to pick 25 microns. We can ease up on the image smoothing strength as well. We'll set that to 1. Select OK. Now again, after you've undergone the pre-processing step, you can simply come and apply a line scanning tool to determine whether those settings will be sufficient. So in this case, it looks like we've eliminated much of the background and we are able to recognize individual cells as distinct. Now, if it seems that your image is blown out, what you can do is adjust using your brightness and contrast settings. For example, selecting neutral takes it to much more tamer brightness. And so here you can see that we'll most likely be able to identify each of these nuclei as individual objects. So once we're satisfied with both the pre-processing steps that we've applied to both text is read as well as our DAPI channel, we can simply add step. Any wells we've imaged, this pre-processing step will be applied to. And so now that we've undergone our image pre-processing step, we can then move on to cellular analysis. This is where we will identify each of our objects and also apply a subpopulation to select out those colonies which contain at least 50 cells. So select the Analyze option. You're going to set up a new image analysis data reduction step. So for this, we want to make sure that our detection channel is text is read. This will ensure that that is the primary mask. So on the left-hand side, what we want to do is optimize our analysis settings. So for our primary mask, which is text is read, we see a default threshold of 5,000. Typically, that's sufficient. However, it's good practice to set the auto at a first pass. Also, deselect split touching objects. Now, under advanced detection options, what we want to do is apply another round of background flattening. Deselect auto and set this again to 2000. Again, set your image smoothing strength to what we use for the pre-processing step, which is 5. And maintain that we're going to use the threshold mask as our primary mask. Now, for our object selection, we want to be able to identify all objects in the field regardless of size at first. So this means setting a wide range. So the minimum object size, we can leave at 5 microns, but for larger objects in the field, we want to set this at high enough to where we can capture those. And I typically use something well above what is needed, such as 10,000 microns. We also want to select include primary edge objects. And as we walk through each of these steps, I like to hit apply just to see how this looks so far. Now, if you're not satisfied with the stringency with which it identified objects, you could always go back, deselect threshold, and reduce your threshold value to identify more signal in your well. For example, if we deselected auto and kept the value at the default setting of 5,000, hit apply, we then were able to capture more of the colony that was otherwise missed using the auto function. And if you're satisfied with this setting, what we can then do is proceed to the next step, which is a secondary mask. The secondary mask is going to use your DAPI channel. This is where we're going to identify individual cells within the colony based using the nucleus. So we're going to measure with the primary mask. We're also going to use a spot counting module. So select that. We want to identify all nuclei, as much nuclei as we can. So we want to set this to 1, The maximum size, we can set that to 50 for now. What I'm going to do is focus on this as we undertake or as we set our parameters. Hit apply. In order to see the nuclei much clearer, what you can do is deselect the red channel along the way. If you're satisfied with this, that you've identified all objects, then we can proceed to the next stage. However, you can see that some nuclei have emerged or have not been identified. So for that, we can go to our advanced setting, decrease our rolling ball size so that we remove a little bit more background, and increase our threshold. For this, we'll set this to 15,000. Hit apply again. In this case, we've made the threshold much more stringent and have been able to separate some nuclei that might have been too close to be previously identified. So once we're satisfied with that, we can move on to the next step. Determine which metrics you're going to calculate. And by default, there is a long list, but for this purpose of the colony formation assay, all we are interested in is counting the number of objects or colonies. In this case, it's called cell count. And we're also interested in identifying the area. In addition, because we're using the spot counting app, we want to know how many nuclei are within each colony. By hitting apply, what you've done is reset the metrics that are displayed on the right-hand side. Now that we've done this, what we can then do is set a subpopulation analysis. And what this will do is allow us to determine of all the colonies in this well, how many contain 50 cells or more. So we want to add a subpopulation analysis. And we will call this colony 50 cells. For this, we will be using the spot count, the values that we derived from the spot count. Add this. And for this, we want to identify all colonies that contain at least 50 cells or 50 nuclei. And what we want to know about this is how many there are in our cell count. And another useful metric to know is what is the area of that colony. So once we hit OK, we can then apply again. And then OK. Now, in order to view which objects have more or which colonies have more than 50 cells, we can simply come down here, and if you want to view them if you want to visualize them a little easier, we can come down to our highlight objects and change some of the settings here. For example, if we click our settings tab, instead of using the default system preferences, we can deselect that, and then we can change these to any color we want. So for all the colonies that have been identified or objects, we can select them and display them in red. For those that are in our subpopulation analysis that contain at least 50 cells, we can select a different color, such as green. Another useful feature is to select or fill objects to visualize those objects. And what you'll see is this identified all objects, as well as those that may not even be a colony. However, because we are only interested in those that contain at least 50 cells, go to your object details, select the subpopulation analysis tab. And what we can see is because even regions that are considered to be an object do not contain nuclei, those are not considered in the final analysis. And we can see that of those colonies that have been identified, only 6 are considered greater than or equal to a 50 cell colony. And if we're satisfied with these cellular analysis settings, we could then add step, and those settings will be applied to all wells that have been imaged. Now, in the case where you have used the colony formation assay to determine an IC50 value for a drug, I will then go on to show you how to build a dose response curve. So once you've undergone your cellular analysis step, what you can then do is represent the data in multiple ways. You can represent the raw data as number of colonies. However, you can also represent the data in terms of the percentage of colonies relative to control. And so for here, what we've done is we've established two different transforms. The first transform is to take all of the replicates of any given drug titration and derived an average from those. In the second transformation, what we've done is we've integrated a calculation that will then derive the percentage of colonies relative to control. Lastly, what we will do is then apply a dose response curve. Now, to do this for your particular drug, what you'll want to do is select your concentration as your x-axis, and then as your y value, select the colony number, which is represented as a percent of your vehicle control. And of course, you want to select that you want to do it at all IDs for all concentrations. And a dose response curve is best representative or best fit as a 4-parameter nonlinear regression. So select that option. We want to represent the values as an average of all the replicates with no weighting. Then you want to name your data set. In this case, I've named it percent colony. Once you hit OK, what will then happen is a graph will be built. And in this particular data set, I have two different drugs, drug number 1 and drug number 2. And what we can see here is the data is displayed as orange means, while all the replicates are represented, as well as the standard deviation as the error bars. And in the perforated black line is the fitted curve. And the red lines is the extrapolated values for your IC50. These values can also be found below the graph right in this drop-down menu, where we can see both all the 4 parameters that were determined to build this curve, as well as the meaningful extrapolations. So for example, for the first drug, what we have is an IC50 of 25 nanomolar, whereas drug 2 has an IC50 of 20 nanomolar. And since we have two different drugs, we could toggle at the top in the graph and choose which graph it is we want to see. Now that we've imaged colonies using the inverted fluorescence microscopy, what we can then do is use that information to build a colony area calibration curve. This is important if you then want to image colonies using a bright field microscopy. To do so, what we will need to do is build a scatter plot using the fluorescence data. Now, to build a scatter plot, what we want to do is expand upon the cellular analysis function. So if you select on a well, go to your Analyze tab, pull up a cellular analysis step. In the well data here, what you'll notice on the right-hand side is an icon to create a new scatter plot. Select that, and you have two options, either a histogram or a scatter plot. And for this one, what we want to make sure is the values that we determined in our cellular analysis is represented in the XY data. So for the X-axis, we want the colony area to be represented. For the Y-axis, we want the spot count data, or the number of nuclei, to be represented. Hit OK. And what you'll see is a distribution of the colonies or the objects in this field and the number of nuclei within them. So you'll see a correlation between the area and the number of cells. Now, what you can do is, this is simply a well-level data, but to apply this scatter plot, or to build a scatter plot for an entire plate, if you have a plate's worth of data, is to leave this window open and hit Apply Changes. I've already done this, so we won't do this again. And so to view the scatter plot data, select it from the dataset drop-down menu. And here what you're looking at is scatter plots for each well in a 96 well plate. And if we select on an individual well, we can see the data from that well. And if we want to compile all this data into one graph, simply select all of the wells, hit OK, then we can see this. Now what we want to do is export this and build a linear regression curve in GraphPad Prism. However, we cannot directly export it from Gen 5. So what we want to do is first export this data to Excel. To do so, instead of viewing the graph, select the Data tab, and then click the Excel icon. What this does is export this data into Excel, as shown here. Now, what you can do is select the values that you're interested in. In this case, we're interested in the columns that represent the area of the colony and the number of nuclei within them. Then select those and paste them into Prism. Next, what we want to do is build a linear regression curve. And the way we could do that is in the analysis section, select the icon to fit a line with a simple linear regression. Since I've already done this, we get this menu showing if we want to analyze the data again. The important thing to know when setting up a linear regression is that I've set the constraint to force the linear regression curve to go through the origin. So once we apply a linear regression curve, what we can see is that we build a graph where we have the scatter plot shown in black dots, and then the linear regression curve shown as a red line. Now, the important thing to know is that we want to be able to use the equation for that line. And that can be found in the results section right here. So right here is the equation. Now, since our y value is the number of nuclei and our x value is the cell area, what we want to do is we want to know what is the area that correlates to 50 cells. So in this case, we would simply solve for x using 50 cells as our y value. So our new equation would be 50 divided by our slope, 0.0004864. And by doing so, what we will get is in the case of this data set, is we've correlated 50 cells to around 103,000 square microns. This value can then be used to build a subpopulation analysis step in Brightfield once we've identified colonies and have also measured their area of their size. We can then set a cutoff for 103,000 square microns as our cutoff that correlates to at least 50 cells or more. Now that you have set up a colony area calibration curve, you can continue on to image your colonies using the upright bright field capabilities of Citation 7. To do so, simply open Gen 5 again. And in this case, when preparing samples for upright bright field imaging, what you want to remember is a key step, which is how you carry out your final washes. So the same preparation applies to your colonies where you're going to fix with 4% paraformaldehyde. You'll then stain with crystal violet diluted in PBS for 10 to 15 minutes. And after that, you're going to aspirate. And instead of using PBS for your washes, you're going to want to use water. But this is because if you dry out the wells in PBS, you'll be left with a salt residue that makes the imaging a little bit more difficult. So to get started imaging with upright bright field, you'll simply open up Gen 5, select an experiment, and create new. Select your procedure. Then you'll want to select the correct plate that you're using. In our case, I've used a CoStar 96 well clear bottom with a catalog number 3904. We're not going to be using the lid, so we could deselect that. And in our actions, you want to select your image and select upright imager. Now, we're only going to select select well for this one. In this case, it's D4. However, if you're doing a complete titration curve, just make sure that you're imaging the entire well. Using the 2x upright magnification, we can capture the entire well with a single image. So we want to make sure we select that. We also want to make sure that we're using our wide field of view capability. So make sure that that is selected as well. We're going to be using transmitted light. However, for exposure, we're going to be setting the exposure settings manually. So to do so, we first want to select the microscope icon to pull in the live view. Select OK. We go to our well of interest. Now for upright bright field, I like to set LED intensity of 1, integration time of 25, and a camera gain of 5. Now don't be too alarmed if your image is out of focus. We could simply then use autofocus to find a correct focal plane. Once we do that, you want to make note of where that focal plane is. In this case, it's 2536 microns. So we want to save these settings. We want to know that focal distance because we then are going to go into focal options. We're going to select fixed focal height based on the bottom elevation. So what we want to do is take the difference of the bottom elevation, 3,300 microns, from that focal height that we found to be ideal, which is 2536. And set our offset. And select OK. Now to make the analysis easier, we want to select cropped image the size of well. This way, we are not using image information outside of the well to analyze our data. Hit OK. Now we're ready to image. So select OK out of the procedure window. Come up and hit Read New. Now you'll be prompted to save your image somewhere. In this case, we're just going to go ahead and overwrite this previously existed one. Yes. Now that our image is captured, we can then select the thumbnail and begin our cellular analysis. For upright bright field, there's no need to do any pre-processing step for background correction. So we simply need to come over here, select our Analyze, set up a new analysis data reduction step. The type of analysis we want to do is cellular analysis. And then we want to select the detection channel to use. In my case, we're going to use the green channel. Select options to specify how we're going to do the cellular analysis step. For the threshold, we can set that to auto. Hit OK. We want to make sure our background is set to light because the background is light. We also want to deselect split touching objects. We also want to fill in the holes in the mask. And under Advanced Detection Options, we want to set our image smoothing strength to 5. For object selection, we want to make sure that we are able to detect all objects in the field. So we want to set that to as low as possible. I typically keep that at 5 microns. However, the maximum object size, in this case, we're going to set that to something well above what we're going to need. So we're going to set that to 10,000. We also want to make sure that we detect all objects in the well, including those that are close to the well wall. So we select Include Primary Edge Objects. And as you can see, the mask has encompassed the entire well, however, is excluding everything beyond the well. Now, I like to do this in a stepwise fashion as I've done previously. So once I select this, I will click Apply to make sure that this is going to be, these settings are sufficient. Now, if you have trouble seeing what is being detected or not, you can come over here onto the bottom right-hand side of the window and modify how this information is being displayed. Deselect System Preferences, and you can change the colors that are being represented. For this one, I like to use red, and for what we'll get to, the subpopulation, we will use green. And additionally, if you select Fill Objects, we'll be able to visualize those objects that were detected a little easier. Now that we've done that, we can proceed with the subsequent steps of our image analysis, data reduction step. So now that we've decided that our primary mask is sufficient, we can go and deselect our analysis for our secondary mask, since we will not be using those. For our calculated metrics, we can deselect all of these and only include the ones that we will need, which is the cell count and the object area. Then we will want to set up a subpopulation analysis to select only those colonies that have reached the 50 cell minimum size based on colony area. Click Add. We can name this Colony Formation 50 cells. We select the area, add condition, and we determined that for CACO2 cells, a colony area that is equal to 102,000 microns, square microns, correlates to a cell number of 50 cells. We hit OK. And from this subpopulation analysis, we want to know how many cells and also what the area of those colonies are. Now, after we've done all this, we hit OK. And now what you're looking at is the initial data identifying all objects. And if you come over here to Object Details on the right-hand side, you can select the subpopulation analysis. And now what we are seeing is, of all of these objects, we have identified 5 colonies that have met the criteria of 50 cells based on the colony area. And once we are satisfied with our analysis steps, simply add this, and then it will apply that image analysis data reduction step to all wells that contain data. For conducting a dose response curve, using a 96-well format is ideal to capture multiple replicates of a given concentration for a large range of concentrations. Once you've imaged an entire plate, as shown here, you can then go to set your plate layout. To do that, you click on the left here, Plate Layout, designate the concentrations. In this case, we have a control, vehicle control, as well as doxorubicin done at various concentrations from 0.01 micrograms per mil all the way up to 1,000 micrograms per mil. Once you've set that, you can then go to Data Reduction and select a dose response curve under Curve Analysis. In this case, this is what has been done here. You will then set as your y-axis your concentrations. Then for your y-axis, you will set your area colony counts. You want to use a nonlinear regression using a 4-parameter fit curve. And you also want to represent the data as an average of all replicates with no weighting. You can represent these as raw colony counts per well. However, you could also represent these as relative to control, in which case you will want a normalization transformation. In this case, what you want to do is select your colony data, normalize to the DMSO vehicle control, represent it as a percentage, and then give your count a new name. Then, based on this, you can then set a second dose response curve where you're inputting that new percentage data. Once you have done that, you could then go over and build your dose response curve, which would display in red your extrapolated IC50 for your drug target. And if you look at the bottom here, what you'll find is your results section for colony count and percentage of your dose response, which is 7.5 nanomolar. We have adapted the colony formation assay using the Cytation 7 cell imaging multimode reader. Automating the imaging and analysis steps of the assay provides a more quantitative method to generate data which requires less analysis time. The assay can be conducted using the established colorimetric application of crystal violet, as well as a new approach using its inherent fluorescent property. There are a few aspects to consider when deciding which method is right for you. If you're conducting the assay using fluorescence, keep in mind that while it is compatible with all Cytation readers, it requires a DAPI and Texas Red filter cube. We optimize the assay using a 4x objective, which requires 4 images to capture the entire well of a 96-well plate. This means that imaging will result in larger files and take longer than upright bright field microscopy. Upright bright field imaging uses the traditional crystal violet signal. The Cytation 7 is equipped with 2x magnification optics, which allows whole wells to be captured in a single image. This means it is faster and minimizes file size. Additionally, because it is conducted using conventional sample preparation techniques, plates are storage friendly. However, an initial fluorescence-based colony area calibration curve is required to analyze the assay using upright bright field microscopy. The Cytation 7 cell imaging multimode reader is the ideal instrument to automate the colony formation assay because it enables both fluorescence and upright bright field microscopy. Please visit us at biotech.com for more information, or if you have any questions or require support, please contact BioTech's Technical Assistance Center.